So yes, my name is Dr. Pat Watson. I work at the Singh Center for Nanotechnology at Penn, and the title of the talk is Quantum Dots and Quantum Dot-Based Devices. And I'm going to give it a chemistry spin. So this is nanotechnology that's enabled by chemistry. The garish colors that I chose for quantum dots and quantum W, this is the text, is intentional because this green and red is actually used in one of the applications, and I'll talk about that later. Okay, so let me talk about the Singh Center. And there's also a reason for that too. We'll get to that in the final slide. So here's an image of it. And this is right around twilight. It's a beautiful building. It was built and finally occupied, or first occupied, or let's say fully occupied in 2014. So it's only about 6 years we've had this running. And it's right next to our physics building and engineering building on campus on Walnut Street. So it consists of a series of labs, 3 big labs in particular. And 2 of them are used to look at things at the nanoscale and also the atomic scale. And we have a lab that is primarily concerned with looking at things with electron microscopes. We also have a unique lab that uses scanning probe equipment, microscopes, like atomic force microscopes, to look at things at the nanoscale and atomic scale as well. But there's one other lab, and this is the one that I do most of my work in. It's a clean room. And it allows us not just to look at these things, but to build stuff at the nanoscale. So here's an image of one of the tools. So this won't make nanoscale devices, but this can make micron scale devices. And this is a printer that allows us to essentially do photography at the micro scale. And I believe the people in this image are from CCP. So we had some visitors from your college. Your colleagues came by in October. They were taking an intro to nanotechnology course, and they came in to build some devices in our clean room. So here is another image from our clean room, and this is a special fume hood that has a relatively simple machine in it, but it's of fundamental importance. We use it all the time. It's a spin coater, and basically what it does is allow us to take polymers and other kinds of materials and in a liquid form, dribble them onto the surface of a substrate. We spin it really fast. We can get these beautiful uniform coatings. And again, this will come up in the end. This is a critical piece of one of the things I'll talk about for the applications at the end. Okay, so this is the required slide. What is nanotechnology? I'm sure you all know something about it. It's looking at and creating and measuring structures that are in this nanometer length scale range. So just to give you an idea of what a nanometer is, there's lots of analogies out there, but one of them is that your arm, if you stretch your arm out from the tip of your index finger, let's say your shoulder, it's about 1 meter. So you imagine if you divided that distance into 1 billion different little tiny pieces, that is 1 nanometer. So another way to get your head around this is to think about the width of your hair. So the width of one piece of your strand of your hair is about 80 microns across. And that's about 80,000 nanometers. So even the width of your hair is extremely large compared to the nanometer scale. In spite of that, you have nanometer scale devices in your holding every day. And those are inside these integrated circuit processor chips that are in your smartphones. So if you have a late model phone, the transistors or the electrical switches that are in them are probably about 10 nanometers across. So if we stacked a transistor and a 10 nanometer transistor and then put a gap between it of another 10 nanometers so we can put electrical connections between it, we could get 4,000 of these tiny transistors in the width of the human hair. And you can imagine then if we have a 2-dimensional surface, we can put lots and lots of them. And as a matter of fact, the chips that are in your phones now have way over 1 billion of these transistors in them. And all of them have to work, which is incredible as well. So nanometer is not the be-all, end-all. There are smaller things that we look at all the time. So we're not at the atomic scale in nanotechnology, but we're pretty close. But so for a typical crystal, let's say for a silicon crystal, the distance between the silicon atoms in a crystal are about somewhere around 2.5 angstroms, or 0.25 nanometers. So that means there's about 4 atoms in a single nanometer. So even, let's say, a 10 by 10 by 10 nanometer little cube of material has thousands and thousands of atoms. So we're still not at the atomic scale, but we're so close to it that we see lots of unique things. Okay, so why do we look at nanotechnology? Well, one reason is, like integrated circuits, for the most part, we do it because it's so small we can pack lots of them together and make lots of money doing that. But there are other reasons why we want to make things small, because all of a sudden the properties change. And one of the reasons is, an important reason, is because now these structures that we build are mostly surfaces and edges. The atoms are, a large proportion of them can be considered a surface and not the bulk of the material. So it changes a lot of the fundamental properties of it. And there's another effect, and that's one that we're going to talk about today, is confinement. When you squeeze this bulk material but turn it into a very tiny little object, there's other limitations based on quantum mechanics that force you to have very different properties than you would in the bulk. And we're going to exploit that with the quantum dots. Okay, so how can we use these properties to do new things? I'll give you 2 examples today. And one of them is being used all the time, and the other maybe we use soon. Okay, so now let's talk about a little bit of physics, I guess. So let's just, or it's really chemistry. So let's imagine, let's say this blue dot here is an atom. Let's say, and it's like something like sodium. So it has lots of core electrons in it, but it has an electron on the outside there, that a valence electron of just 1, let's say. And that gray line, horizontal line, is representing, let's say, the energy of that electron. If we bring another one in and connect them together, we're making a molecule now. And we have 2 electrons now that we have to account for. And with the exclusion principle tells us that we can fill 2 of them up per energy level, but we can't put any more in there. So if we add another atom, we're going to get more possible states, but we can't put all of them down at the bottom level. So we have to just keep on populating this as we go more and more. And here, if we add another one, we keep on adding more states, but also filling it up, the bottom ones at low temperatures anyway. Okay, so you can imagine if we do this and now put 10 to the 20 of these atoms all together, what happens is we can represent it by this plot at the bottom here. So this is maybe another view of it. Let's think of like a crystal. Think of a big cubic crystal. But now the atoms are really far away from each other. And that's the right-hand side of this plot, atomic spacing. And we're plotting energy on the vertical axis. And this is this lower plot. So if they're all separated from there, they don't really touch each other, they don't feel each other. All the energy levels are about the same in all these atoms. But as we push these things closer and closer together, they have to interact, just like our line of simple atoms on the top there. And we get lots and lots of energy states, and we start populating them with lots and lots of electrons. And we're squeezing these things together, and as we get these things closer and closer to atomic scale dimensions, we get these really interesting properties. So this is just another way of looking at what happens. So these blue regions in this plot are lots and many, many, many electron states, but there's so many of them, they're so finely, the distance between them is so small in energy that they look like a continuous band. And that's what we call these bands. Okay. So let's look at this plot again, and let's look at it for one particular, let's look at silicon. So silicon has 4 valence electrons. So we have the S's and we have p orbitals, and this is in the 3rd shell, I guess. And we can imagine that these 4 electrons are going to, as we squeeze everything together, they're going to start splitting and forming all these different unique electron states. And if we get to that magenta distance there, let's say that's our equilibrium position where silicon likes to be as a crystal. And at that point, we have 2 bands here. We have a valence band at the bottom, and then we have this energy gap, and then we have a conduction band. Well, it turns out that for this valence of 4, the number of states in the valence band is exactly the same number of valence electrons. So we can fill them up, that valence band, all the way to the top, but we don't need to go into the conduction band because we don't have any more electrons. So all of the electrons are going to sit down the bottom there. And this is what makes a semiconductor. So we have this gap, we have a conduction band, we have a valence band, we have an energy gap between them, and we have the valence band completely filled, the conduction band is completely empty. And this makes these incredible, unique properties that allow us to build electronic devices and also photonic devices. Okay, so let's look at a periodic table. I guess they're no longer called these group 4s and things like that. Now they're named 1 through 17 or 18 or so. But this used to be called group 4 with the arrow here. So it's carbon, silicon, germanium. And the reason is because in the crystal structures that we look at, they have 4 valence electrons. So carbon, when it looks like diamond, the diamond structure, it looks very similar to silicon, germanium, and one of the forms of tin. And they all look like these semiconductors. We have the 4 valence electrons, we have a valence band filled, we have a gap, energy gap, and we have a conduction band at the top that's empty. So one of the cool things we can do is that we can take binary equal amounts of, let's say, a group 3 material, which is shown by the boron column, and of group 5 material, which is the nitrogen column, and we can mix them in equal quantities, and it looks just like silicon or germanium or tin. We get the same kind of properties. So the group 3 and the 5 together look like 2 4s. And these are also semiconductors, or most of them are, when we mix them together. We can even do, and so here's an important pair, gallium nitride. This is all over the place. You're using this all the time. This is the fundamental crystal that's used for visible LED lighting. That's all around now. Okay, we can also take group 2, and the zinc, cadmium, mercury is sort of a group 2. It's a transition metal, but they really have 2 valence electrons for most of the time. And then we have the oxygen. So now we can do the same thing. 2 and 6 looks just like 2 group 4s, and they also make semiconductors. And here's the pair that we want to talk about today, cadmium and selenium. We make cadmium selenide. It's a semiconductor, and it has really interesting optical properties. So let's talk about optical properties. Okay, so a lot of these compounds that are semiconductors, a subset of them are called direct bandgap semiconductors. And the cool thing about them is that we can get light out of them. So applications using these direct band semiconductors are all around us. Laser pointers, they're all laser diodes. These are semiconductor diodes that we drive current through, and we can get beautiful colors like red and green lasers out of them. If you have FiOS, or even just talking long distance over fiber optic communications from country to country, you have to use optics and not electronics to get your signals from one place to another. So even in your house, if you have FiOS, you have laser diodes that are made out of these compounds like indium phosphide and gallium arsenide to detect optical signals and to send them back out again on the fiber. And then, as I mentioned before, gallium nitride, visible lights. So here's some examples at the bottom there. These are visible LEDs made out of gallium nitride or alloys of aluminum gallium nitride. So how do they work? Well, if we have an electron on the top there, and we do it electrically, we can fool around with it, and also a gap or a missing electron down below in the valence band. If they're direct band semiconductors, when they see each other, they will drop down and form a photon, that red arrow popping out. There's another thing, a way of this, that's called electroluminescence. There's another way of getting light out of these things, and that's what we're going to exploit. It's photoluminescence. So if this blue arrow represents like a light that's coming in that has a characteristic energy that's larger than the band gap, we can kick that electron out of the valence band, and it's going to drop back down again. And when it does, it's going to give us a unique color, and that's represented by the red arrow there. So this is the second way, this photoluminescence is what we're going to exploit with quantum dots. Okay. So all the other applications that I've shown you here before, how do we change this energy gap and how do we change the color? We do it by changing the alloy composition. So let's say if we wanted to change the wavelength of the laser diodes that we use for gallium nitride, a laser, let's say a laser pointer, we would change the composition of the gallium, maybe add aluminum to it. So it's now aluminum gallium nitride. They're both group 3s and a group 5. There's another way of changing that energy gap in that color, and that's by confinement. And that's the trick that makes quantum dots unique. So, confinement. If you take a course in quantum chemistry, you'll learn about it. The first thing that you probably have to do as a homework assignment is to work through the math of a problem called a particle in a box. And this is the same sort of thing. And what it basically says is that if you confine an electron that's bouncing around inside a solid to a very small region, and you limit it by putting big potentials at the edges of it, you can change the energy states that it can go into. So here's what happens. So this plot down here is showing energy versus, don't worry about the horizontal axis, it's called density of states. But what I want you to concentrate on is the leftmost one is showing a bulk semiconductor. And that energy gap is that little white region between the blue valence band and the red conduction band. And that tells you what the color of the light that will come out of it. If we make that bulk material into a quantum dot, like the middle one there, then what happens is that this confinement forces these things into discrete little states there. And the distance now between that SE and the SH is a little larger than the bulk material. So it's going to higher energy, and it's going to give a bluer light when it comes when it emits light from photoluminescence. And then if you make a super tiny one, like the rightmost one, that gap gets even larger, and the light gets bluer. So the cool thing about this is that we don't change the chemistry. It's exactly the same material, cadmium and selenium, equal amounts, but the size of the structure determines what the color is that's going to be coming out of them. Okay, so now we can talk about a little bit about chemistry. Okay, so how do we make these quantum dots? Well, we have to get this cadmium and the selenium into a solution, and liquids are great for doing chemical reactions because they allow these things to bounce around, connect with each other, and do it in a reasonable time frame. So to get the cadmium and selenium into a liquid, what we do is we surround it by these materials called ligands. So the ligands we use are organic molecules, and they may have long carbon chains, for instance. At the end of them, they have a very polar kind of structure, and that attaches to the metal like cadmium or selenium or gold. And that allows us to hide the fact that we have gold floating around in the solution, because your solution or your solvent only sees these large organic groups that are popping out of the edges. And that's sort of what this picture is representing here. So in the middle of it is a metal, but now it can float around in organic material freely and look just like it's in solution. So really it's a colloid, I guess, but it looks like a solution essentially. Okay, so we use these long chain things like oleic acid to get our cadmium into solution. And then we use another material, trioctyl phosphine. This has long 8 carbon long chains on it popping out of it. And that's how we get the selenium into solution. And then we're going to use this solvent to get everything running called octadecene. And it's a long chain, alkene it's called. And it's a organic liquid. You can get it for like $30 a gallon or something like that. And what's really good at is it doesn't volatilize. So unlike other organic solvents that you probably work with, maybe like hexane or something, it's not going to blow up when you heat it up to 200 Celsius. So that's why this is so useful. And it looks almost exactly like oleic acid and oleamine. So these things all can mix in together very easily. Okay, so let's go drill down a little bit more and look at some more detail here. We dissolve our cadmium, as I mentioned, with oleic acid. And it looks sort of like this image at the top right here. We have this non-polar tail of the organic stuff. Then we have this polar head that might have like oxygens and things that are easy to ionize on the end there. And it sticks to our cadmium. And also, well, what it'll do is because of thermal things, it's not a great tight bond. It'll pop off all the time too. So it's just popping in and out all these little things around the cadmium. And then selenium as I mentioned before, are dissolved in this other material, trioctylphosphine. They're doing the same thing. They have this nonpolar tail that allows it to get into the solution, but it's popping on and off thermally as things are bumping into each other. And every once in a while, they're going to pop off, and the cadmium and selenium are going to see each other, and they're going to attach. And they have a preferred, lower free energy, so they're going to love to stick together. So then these ligands aren't thrown out at this point, because they also see the whole crystal that's forming, and they're going to actually surround that crystal, and they can control the growth rate of that as well, and the shape of these quantum dots. So these ligands are hanging around doing stuff all the time while we're cooking this. So the image at the bottom is a molecular simulation, and this is from Oak Ridge. They use this supercomputer to look at every single atom in this little tiny nanocrystal, and also the ligands around it to see what the properties are. And so that's some pretty cool numerical quantum chemistry that's being done. And this is the exact same system that we're looking at, cadmium selenide with ligands, organic ligands around it. So here's a cartoon of the process. So we use this in our laboratory course in ESC 536 to demonstrate quantum dots and to use them potentially for device applications. So we start with a hot plate. We have a little Erlenmeyer flask. We put in this octadecene, our solvent. We heat it up to 165 Celsius, and then we inject our precursors, and we have the cadmium and selenium already in solution. We inject just a little bit in it, and almost instantly you see the solution start turning orange here, and that's because we start absorbing photons, the light in the blue region. And this is characteristic of all kinds of quantum dots, not just direct band gap ones. Okay, and then we just with time we just withdraw samples. The longer it's in there, the larger these crystals will grow. So now we can get a whole variety of quantum dots. They're chemically identical. They just have different characteristic sizes. And here's a plot. This is from a paper where we took some of the recipes from. And they can demonstrate all the way from this beautiful deep blue color to red using cadmium selenide. And you get all these colors of the spectrum. We've never been able to do that in practice. We can get parts of this, one part or the other, but we haven't been able to get it in one run. So we don't know how they did it exactly. Okay, so now let's go to the real hardware. So here's the materials we're using. I wanted to emphasize this because these are really off-the-shelf kind of things. There's no complex things. You can buy this from chemical companies, all of the components. Here's one thing. So you can almost do this at home, but please don't do it, because cadmium and selenium, but cadmium especially, is a carcinogen, and it's awful material. So you want to do this in a fume hood, and you want to make sure you have proper personal protective equipment to make sure that you don't get harmed by it. But it's super simple, which is really cool. Okay, so here's the materials we use. So we're using this oleamine, as I mentioned, to get the cadmium into solution. So we mix it in, heat it up with cadmium acetate, which is these little green crystals. And it takes the acetate part off. The oleamine sticks to the cadmium, surrounds it, and gets it into solution, into octadecene. And then this acetate apparently becomes acetic acid and just evaporates. The selenium, even at room temperature, will mix with our trioctylphosphine. And those are our precursors. We put them in the octadecene, which is the solvent in the middle there, and we cook away. So here's the apparatus that we need. Again, super simple. We have a stirrer hot plate, we have an Erlenmeyer flask, we have a thermocouple to control the temperature and maintain it, let's say, at 165. And then to get our samples out, we use these little test tube racks here in blue. And we put little test tubes in there. We use that pipette with the yellow bulb on it to withdraw it from our Erlenmeyer flask and drop it in there. The test tubes are sitting in a bath of water, and that allows us to quench it. So as soon as we take it out of that flask, drop it into the test tube, the temperature drops so dramatically that essentially it stops the growth rate of the quantum dots. And now they're nice and stable, and they'll remain at their size indefinitely. Okay. And then we can just, with time, just withdraw more and more, and we get larger and larger quantum dots. Okay. So here's an example. So we put these in these little cuvettes to make it easy to do characterization. And you can see on the right, we're using a black light or ultraviolet light And you can see this beautiful green color coming out of this from the quantum dots here. So they're taking the ultraviolet light, creating electron hole pairs, and then the electrons dropping back down again at the very specific energy determined by the confinement effect. And we get this beautiful green. Other samples from this batch could be red or blue. Okay, so let me just talk a little bit about characterization. So here's some spectrum. This is really a simple machine. We just have an ultraviolet light source, and it's a gallium nitride LED, believe it or not. And we shine it into our little cuvette, and we have fiber optic cables that bring it over to a diffraction grating to allow us to split up the spectrum. And then we can see what the intensity of light is versus wavelength for these materials. So here's a typical plot, and we're plotting the intensity of the light versus wavelength on here. So the little peak on the left is from our light source. That's from our ultraviolet light source, which is the gallium nitride LED. And then the big peak, that's from our quantum dots. So the cool thing about it is that this is relatively tight. It's a relatively narrow band here of light that's coming out of it. That means all those quantum dots are about the same size, which is one of the really neat things about it. We don't get this big dispersion of quantum dots that are a whole range, and then you get a whole blend of colors. We can get real specific colors with this, except for that bulge there. We don't know what that is on the right-hand side. That is one of the cool things about this process is that because of the relative rates and the way these ligands pop on and off, we can make them all about the same size. Oops, sorry, wrong way. Okay, so what can we do with them? So there's two applications I want to talk about. One of them is being used right now, and at least one version of this, and it's quantum dots are being used in displays, and you get these incredible vivid colors out of them. And for the very same reason that you see these beautiful colors coming out when we hit them with ultraviolet light and look in a spectrometer. Okay, and we have the potential of making these things any shape to these displays. They could even be flexible. Let's talk a little about the details then of building a display like this. So here's how it works. Even conventional displays work the same way. So in the top right there, we have light. We polarize the light, and then we use something called liquid crystals. And we can, by applying the voltage, we can make these crystals twist, and they'll change the polarization state. So we can actually make this light turn on and off. And that's how we switch things. And if you shine it through 3 different colored pixels that have different filters in them, you can get the things to emit 3 different colors per pixel. And now you can make big arrays of them and make pictures and do things like video games and movies with them. So with quantum dots, we're replacing those filters with our little quantum dot stuff. And the reason is because the color is so intense, it's so narrow, we can get beautiful colors with a true color approaching the true color of the objects that are being imaged. And we can do this by using LEDs. The light emitting diodes can be gallium nitride, can be giving off blue, so they'll naturally turn on blue. But if we send it through, let's say, our green quantum dots, we can turn that blue light into green light, and we get this intense green color and red color. And then we can mix them all together and get any color we want. So this is being used now in some versions of quantum dot TVs, QD TVs. Okay, there's another application that this is, let's say, in the works. There's this dream to make wearable electronics that can allow us to do things like monitor do biometrics and look at things like environmental stuff, and also do calculations and do predictions. And the way to do that, one of the things that might be very important is to make sure that these things are flexible. So silicon, which is like the primary substrate that's used in the chips that are inside your phones, it's very hard and brittle. It's not going to flex. But if we could build devices that are on the flexible kinds of substrates, we could wrap them around, put them in clothes. So here's an example. For instance, it's a cool image on the right there. This is an important material science journal, Advanced Functional Materials. And this is a special issue they had on wearable electronics. On the lower left, this is from a company called FlexEnable, and this is not real. It isn't working, but you can see in principle it would be such a cool thing if you could actually build a computer that could wrap around your hand and be nice and soft. Okay, so why quantum dots? Well, we're not really using these special properties of the quantum dots, that, you know, this quantum confinement, things like that. We're using the fact that these quantum dots are semiconductors, but also we can get them into a liquid. So this it just gives us a whole new way of building devices that we never had before. So some of the advantages. We could spin coat these, and remember when we talked about the spin coater in the very first couple of slides, I'll talk about it again. Allows us to get these onto the surface of substrates very easily. And there's no other material that allow us to do that except quantum dots. And we can put this on plastic substrates, like flexible ones, like the image there. This is Kapton, this material. So it's a nice tough polyimide polymer, and you can heat it up to like 300 Celsius without damaging it. So you can fabricate devices on this, and everything's nice and flexible, and the temperatures that you'd need to build silicon devices, like 1,000 Celsius. So we'd never be able to use plastic as a substrate. So this is one of the cool things about quantum dots. So there are other ways, people have been exploring other ways of making flexible electronics. One is to use this low temperature amorphous silicon or like organic semiconductors, but it turns out these quantum dots and the devices you can make with them might work much, much better than these other materials. So that's why it's so exciting. So how do we get, even the displays, how do we get these quantum dots in the liquid onto our surface? This is the spin coating process. So remember that image I showed you in the beginning here. Here's a researcher. He's putting a chip into a bowl there, and it's being held onto this rotating stage. And then we start spinning it at high speed. We dribble on a little bit of liquid, and it spins out, makes a beautiful uniform coating. And the solvent, there's so much surface area, the solvent now evaporates away, and now we have a solid on there. So you may need to bake it too, but it's an easy way of getting our materials on there. So we use this all the time for photosensitive polymers and all kinds of applications in nanofabrication. But this allows us to put semiconductors on a surface just by spin coating them. So this is new, and this might be a really cool technology for the future. And that's how we might be able to use this for wearable electronics and even these crazy displays with different shapes. Okay. So the devil's in the details. This is a transmission electron microscope image. So now we're doing a nearly atomic scale imaging. And those little globs there are some nanocrystals, nano quantum dots, cadmium and selenide. The marker there is, I believe, 2 nanometers. So these little guys need to connect into a single chain to be electrically active. So we still have to figure out how to do that well. And sometimes they just do it by multiple coatings, and eventually everything just sort of averages out and they all connect together. But there's lots and lots of things to do. So lots and lots of research to be done. And now that is the end.